Ah, another draft physics video. Yay. So author today linked to this closer to the truth stuff, and so this video was interesting enough, but some of their other videos all seem to have the obsession with a conversation about God, which I don't see any purpose in. So I don't know how many others I'm going to watch. But anyway, so this one's basically just talking to different physicists about their understanding of what a law is, and a few of them, or a rule. Um, And a few of them think we just make them up, that they're not really something we discover about reality. And this one's one of them. And they're mostly the quantum people, of course, who don't think they're actual things that exist as something you can describe into reality and accurately describe it. And the fact that we don't accurately describe the laws would be my argument. That the laws aren't the problem. The fact that there is law, in the sense there are rules to the function. The things have properties and they're limited properties. The universe isn't made of things that have unlimited properties. They're made of things that have limited properties. That is, limited ability to do limited things. And that can only produce a certain kind of permutation. And everything isn't possible. Just certain things are possible. And we can understand those possibilities, and more likely we can understand probabilities if we understand those rules correctly. And so I didn't like any of this conversation in this video. It was really, I think, really an example of why physicists have got it so wrong.
And the same laws seem to apply. So that aliens can observe the same thing, but have totally different laws. Do you really think so?
You really think the aliens would have a different law to describe the same
Different,
phenomenon?
a different phrasing, so different law meaning a different framework, just like.
Okay, it's like, okay, so something like the inverse square law, I would argue, is really reliable truth. That Newton discovered that this is the relationship that happens in terms of how force, and Newton thought of it as a force, emanates from bodies. It happens in this inverse square law rule. Okay, and it has to do both with forces like gravity and forces like light emanating from a spherical source.
Feynman's framework and Heisenberg's Schrodinger's framework are different, right? The equations in the end are the same. In other words, the predictions are the same, but the concepts that they use of what's going on are different. Also,
Okay, but the concepts aren't different. The underlying math isn't any different. So that's the whole point. It's their interpretation of the law and its scope, but nothing about the law is different.
so Einstein's theory of gravity is not such a good example because Einstein makes different predictions than Newton does, right?
Right, but Einstein could be argued is not a law. So again, you could say there are pieces of Einstein that are laws, just as pieces of what Newton said are laws. The fact that Newton said force equals, mass m1 times m2 or plus, you could argue that that wasn't a law, that relationship, in the sense that that misidentifies exactly what force you're measuring. And if you want to know the particular force, you have to ask a more particular question.
But if you look at our everyday world, if we weren't technologically advanced enough to watch the light from distant stars as they pass the sun during an eclipse, or make other of the just hand.
Right. So then, a vague reference to the lensing of light, which again is stated to be a truth, but it's a truth on a shaky foundation. It's weakly evidenced. And that's part of the problem, is you take things that have weak evidence, you define them as a truth, and say this is the way reality works. So you take something like Heisenberg, which is an idea, okay, that somehow photons and electrons and protons and even atoms don't have a location, a specific location, or you could interpret it as the law would be they don't have one that we don't have the instruments required to actually know its position. Now, to me, the sensible law would be, yes, they have a position, we don't have the instrumentality to be able to, at any 1 microsecond, detect their actual position. That would be a sensible law. They have a position, would be the sensible law. The insensible law, in my opinion, is to assume they don't have a position because you're incapable of measuring it.
Full of experiments that we have that can test his theory. For anything but that, his theory makes the same predictions as Newton's theory in our everyday
But
world.
that's different. That's different. That's one is a refined, deep refinement of the.
Well, you could call it. You can call it a refinement, but it's not really much of a refinement. It's a.
So yeah, but see, that's the whole catch here, is that people don't understand what Newton is. Newton is the inverse square law. There's not much else to Newton's equation. It doesn't mean anything except for the inverse square law and this idea of a gravitational constant to actually give the force an actual, weight. But outside of the necessity of the gravitational constant to actually create something that you could understand as a actual per meters per second kind of a thing, or an actual force, to convert it into an actual force, the concept that gravity is basically the inverse square law wins all over the place. And that your mass is a function of your gravity, and that calculation is quite simple. The distance from the gravitational source, and recognizing the mass of the object, and the rest of the math does itself. There's no law necessary beyond understanding how the force changes with distance, and that's the inverse square law.
It's a blowing up of one theory, replacing with the other.
Okay, so it's not blowing up the inverse square law, because bent space, the fabric of space, is exactly the inverse square law. The inverse square law is the fabric of space. So it's in no way blowing it up. It's just, again, he's perfectly accurate to say it's just an advancement on Newton. It's adding to Newton. It's not subtracting from Newton.
So Newton says they're forces. Einstein says space-time gets curved. Right.
Right, and now we're stuck in this other ground where as soon as now they invented this gravitational wave crap, now we have forces back into Einstein's equations, apparently. So again, now we're creating energetic forces that somehow travel across space, and in some other way than gravity travels across space. It's not gravity, it's a force made out of energy.
It's two different inventions. Totally. Two different inventions. Some alien probably has a third invention.
Oh, again, but that invention would still be the inverse square law. So with this, in my opinion, this guy just totally misses the point. That the point of the argument is that the inverse square law is a good law. Now, people can convert it into bent space and throw time on top of it and say it's some other thing, but the inverse square law part of it are still the same. So that part isn't changed because other people decide to play games with it. All right, somewhere around 1730, this guy says some crap that I didn't care much for, but we'll go 1750.
They haven't found any way to construct, theories in which causality is slightly violated, so you wouldn't notice it with observation. But in general, people have been willing to give up almost, in some cases have been forced to. After all,
Right, so they give up this notions, he called them notions or some other kind of thing, of causality and different things, and things that should be in the right order of time, and all of this stuff can get sacrificed because something else works. And my argument would be that's exactly the road to ruin, because instead of figuring out why there's not a consistency with the underlying law or principle that you know to be pretty solid, maybe you should find out why there's an inconsistency, not find a gimmick to get around the inconsistency.
went through only 80 years ago a revolution in physics with the birth of quantum mechanics that forced us to give up some of the absolute obvious assumptions that we made about physical reality.
Right, and they weren't just assumptions. Obviously, they were conclusions based on repeated evidence, and basically the steel ball would hit you in the head, and we know the steel ball didn't go to Pluto before it hit you in the head. So yeah, those kinds of sensible things where you knew that every possible path wasn't the path that it was going to take. It was going to take the consistent all the time path. So again, these, the solid truth is that, and even Feynman will recognize the solid truth, that he can say it takes all the possible paths, but if he was to cut a piece of mirror, he knows that if he's going to reflect light at a certain angle and it's going to get to a certain place, he knows it has to hit the mirror in that spot. He knows it's not going to hit back here, and the light won't go backwards and then bounce forwards. He knows that's not going to happen. And yet he's saying it's somehow logical to do mathematics that includes that as a possibility. And he should be saying, well, no, there's obviously something wrong with me putting in here possibilities that aren't really possible. They can't and won't happen ever.
And so I have a feeling that if it were to work, we'd be willing to give up any principle you could possibly imagine.
There's a
Right. So this obsession with predictions and working, whatever working means. That is, we get something out of it or something. We can now believe in. We can build Legos and stuff. We can do stuff because we think we're seeing something. Now they're going to try to build, a satellite that can use gravitational lensing to somehow see further into the universe. Well, if the principle is wrong, your satellite's not going to see anything. But that won't stop them from finding it, no doubt.
common feeling that when we have mass, we see things that have mass. We have
There we
mass
go.
that we instinctively know what it is. But an understanding of fundamental physics shows that our intuitions are not necessarily correct.
Yeah, I mean, for example, well, one of the nicest advances in our understanding of that occurred, 30 years ago with the theory which I was involved in, the theory of strong nuclear force. That's the force that holds the quarks together, makes up the nucleus, that makes up the center and the mass of the atoms that we're all made out of. So, and those quarks actually are almost massless particles themselves. So if we now understand where most of your weight comes from, maybe 95, 96% of your mass is simply energy. So you remember Einstein?
Okay, but it's not energy in the sense that he's going to say it's a particle or it's a thing moving. It's going to be some kind of field. So again, it's not a very useful definition to say it's energy when you're just going to call it a force that has no mechanism. And that's all he's talking about again. So now it's just this force that somehow the quarks have, because I guess the Higgs boson gives it to them. And now they have this force, and now they're creating a pressure with this magical force that doesn't have any constituent.
Einstein taught us that E equals mc squared. If you have a massive object, you can extract a lot of energy from it, like nuclear reactions. But
Yeah, so it was already something that was given away a long time ago, in the sense there was a giveaway to this, that we kind of knew this as soon as they made an atomic bomb. It was kind of verified, kind of made obvious that there's a lot of stuff going on inside of those things called an atom. There's a lot of pressure of some kind, a lot of will to expand, let's call it. That we could identify, and we don't have to sit there and say it's nothing. We can say it's a something.
right way, the other way you can think about that formula is that mass is simply energy. And now we understand.
Yeah, well, I would say it's simply momentum, okay, of the smallest bits in the universe, these force bits, the quanta.
Understand that our mass, our weight, is simply the energy of these quarks that are being held together by this nuclear force and confined to live within this nucleus.
Right, so there's a force and then a force. There's one force that emanates from them, another force that compresses them. And neither one of those forces will be described as something real, so no point. But I mean, I just wanted to get to the mass subject because I just thought I would do a simplification of just explain how simple it can be and how simply you can understand what's really happening in the universe. So, to the blackboard, the whiteboard, the white paper, the yeah, well, what I'm going to write on. Sorry, my voice is a bit something imperfect. Yeah, look, there's my hand. I gotta change the color. That's kind of neat, green hand, isn't it? Green hand. Alright, so, well, maybe I'll draw bigger, just for the hell of it, because it's a big space. So my idea is that, okay, you have these force bits, and I analogize them to just this simple thing. It's an arrow. Now, what exactly it is, it doesn't matter. It moves the speed of light. So it has one consistent speed, and there's just a zillion of them. And well, just for the sake of being honest and being clear, there's two types. Okay, so you could just say they're round and square, or you could say red and black. It just doesn't matter. There's two kinds of them, and they're exactly the same except for that one difference, that polarization difference. Whether it's a shape, like they could be, they could be an opposite in some way. This one's this way, this one's this way, whatever. It doesn't matter. Well, that didn't show up on the paper. It's the idea they could be polarized this way, they could be polarized this way. They could be circle and they could be square. The point is they're two different things. All right. And they only exist in one dimension. So they only have momentum in one dimension. They're not moving this way or this, well, front to back would be their orientation, but I'm just saying left, right, up, down. They don't move in those directions. They just move in one direction at a time, in one dimension. So it's a one-dimensional, and it equals one mass, let's just say. That's the mass in the universe. That's a mass unit. And everything else, more complex matter, has that stuff, but moving in all three dimensions. So it's got these little bits moving in all three of the dimensions, or all six of the whatever sub-dimensions of what would be the 360 degrees or whatever of a sphere. So they're spherically material things like us. We have these little bits moving in all directions, which gives us solidity, which means we have sides. We have a front and a back. We have a side, a left and a right, and then we can move forward and we can move back and all that stuff in any one of those dimensions. So what's really happening in the universe is just the movement of these little arrows, the collection of them in places. And so the idea would be is that even if you saw the matter bits, the electron, the proton, let's draw them as different colors for the hell of it, and the neutron, which would be the combination of the two, presumably, I would argue anyway. So we can almost negate conversation about the neutron. Yeah, too bad this pen isn't thicker. But, life is what it is. Unfair. Yeah, you really can't see the colors anyway. I have to do something about that. Got the good lights on here. I don't know why it doesn't show up a little better than that. But anyway, not going to fret over it at this moment. So this is the proton. This is the electron. Whoops. Well, it doesn't really matter. And this is the neutron. So this is the neutron. This is the electron. All right. The idea would be is that these things, you could say they have no mass. I think they have to be made up of mass. I think they have to be these arrows trapped. But let's just say we gave them zero mass and zero substance. And then the real trick of the universe is the only way these arrows could hit each other is they have to hit one of these matter bits for the forces to interact with each other. So there'd be two competing little arrows would hit, and one would say go this way and the other one would say go that way, and so then it would go neither way. But if, say, 3 arrows in a row hit from similar directions on this one, then it would go in some direction because it got hit by 3 and it will move in that direction. And that the only thing that moves anything is these little force bits, that they're the only active player, and that there's rules about how they interact in the sense that they essentially, to create the confinement of this bit, their rule is that if they hit it, the momentum is absorbed in the sense that there's an exchange made, and the exchange is going to be for this to go this way, for something. I'll draw a new picture. For this to move this way, the bit hits it, and what it's basically going to do is it's going to hit something going the opposite way. So in a sense you could see that this would reflect off of this, so there'd be just like 2 arrows going this way, and you just get a pure reflection. So inside this thing, the arrow went from going this way to going this way, which means a net going this way, and out here it went from going this way to going back where it came from, which will in all likelihood is going to end up hitting another electron or some other object, and then it's going to end up reflecting right back again, hitting it again. And that's how you create pressure. And so when an atom is formed, what's happening is these things are getting smashed in close proximity to each other, and there's a bunch of these little bits that'll end up between them, and that's the part we're measuring as mass. So the thing we're measuring as mass is really this force that's trapped between the protons, the electrons, and the neutrons. And the rules of communication between them is that, say, if a black one is coming out of an electron, it's going to take a perpendicular direction out of the electron. So it can go in those four directions. And the rule about which way it's going to go is going to be dictated by laws of probability in terms of what its previous condition was. How many bits it has going in a certain direction will dictate which direction it'll choose of those four. But I want to get into that complexity. But the idea would be, as you can sort of get the idea that if it takes a right turn from here, you'd end up with creating a circle. The force is trapped and it just stays inside the atom. But there's a lot of it. So a lot of force is taking these paths, traveling these directions. And that's what you're releasing when you break atoms and create nuclear bombs. And the rest of it is you're releasing all this stuff trapped between the electrons and the protons and the neutrons. And it's this stuff that is going to go into the world, going to be released. And it'll be released as different kinds of energy, and one of the simplest energies it would be a gravity kind of energy. I would argue that a nuclear bomb probably does create a repulsive gravitational force that isn't electromagnetic. But then it'll certainly create lots of other force that's trapped in here in the form of visible light and other electromagnetic pulses, where you just have force at a period, force coming at a constant frequency, and that's your photon. And the tighter that frequency, the X-rays, gamma ray, higher, the tighter the frequency, the higher on the electromagnetic scale. The lower, then it's more like radio waves and other kinds of electromagnetic radiation. So anyway, but it all just starts with this one thing traveling in one dimension, and you can logically kind of understand that, yeah, that's sort of all you need is something to create pressure that forces this stuff to move, and then once it gets into relationships with each other, you just need a couple of rules regarding how those relationships are formed, and you'll end up with a basic function in the end. And the big picture, is that on the human scale, that what's going to happen to these big objects is a force has to go in, and they'll acquire it, and they'll move because it becomes trapped inside of them. So if it goes in, it gets trapped inside of them, and it'll give them a bias in that direction, and they'll just keep moving in that direction until that bias is gone. And that like when we measure mass on Earth, we're not really measuring which way the thing's going. Like if I'm standing on Earth, my real velocity could be all kinds of directions. And the only thing that makes the measurement meaningful is that whatever two things I put on the scales, they're also, say the real velocity is this way. They're moving 1,000 miles an hour this way or something. What I'm really going to be measuring, though, is the difference between them in terms of where everything else is moving, how much three-dimensional mass they have that's not going in that direction, because that direction won't be measurable because they're both going that direction, including the scale. The scale is going to be going that direction too. So there won't be any way to measure any difference in that direction, and all you can measure is the collective differences in other directions based on what, say, something like gravity is doing. And that'll tell you how much mass it has, is how much gravity actually is hitting some portion of this, these weight elements. How many of the bits, the matter bits, so let's just understand, let's call these force bits FB, and then the matter bits are the electron, proton, and the neutron. These are the matter bits. Okay, and the what you're really measuring on a scale is how many of these matter bits, because that's what's going to collect the force. That's what the force is going to hit and interact with. If it doesn't hit a matter bit, it's going to go straight through and do nothing. But if it hits a matter bit, it's going to end up in the network that is the matter, and it's going to propel the matter in the direction that it was going. It's going to, the matter is going to possess the momentum. And so mass is really just a collection of these little bits of momentum. And everything can be explained with this as an understanding that the core rule is that there's just these simple bits, and that their force, and if you want something to move, it has to encounter force, a bias in the force. It has to be hit by more stuff going this way than that way. I mean, to move it that way, I have to hit it with more stuff going that way. Or there has to be less stuff hitting it from this side. But it's just an imbalance every time, an imbalance in the pressure. So I don't know if there's anything else I need to say. But this is what mass is. Mass is this this bit of momentum is a bit of mass, in the sense that it's a bit of force, and all you're measuring is you're just measuring how much force something possesses when you're measuring its mass. And so if you were to measure a photon, it would have no mass in the backward direction, obviously, no mass in the sideways direction. There's no mass. There's only mass in the one direction it's traveling. It can't hit a scale in any direction but the direction it's hitting. And that's really how what you're trying to figure out, is how much stuff do you have pointed in the direction of the scale. And only a material thing can have substance in that direction. It certainly has mass in all the other directions, and what you're just measuring is relative differences compared to something else. What's its mass? What's the density of arrows in this direction? And those arrows are going to be collected by being exposed to gravity. Gravity will be absorbed by your bits, and the absorption, the amount you absorb, will be indicated on the scale. The scale is really just measuring how much gravity did you absorb. That's your weight. How much force did you absorb? And you absorb more force if you have more of these matter bits to trap it between them. Yeah, that's probably, I'm going to keep it simple, stupid. So first try at this drawing thing. It doesn't look too bad, but yeah, just maybe I can, I'll have to see if I can lower the camera, which doesn't seem very likely. Not in any easy way anyway. I mean, I suppose I could put a lens in it. Let's see, if I put a lens under here, well, that might be better. So I'll put a lens on the lens. Maybe. Yeah, I don't know, it gets kind of complicated. Yeah, that's a more better. That would be even better, I guess, is something. I don't know, I have to work on it. Okay, so it's still imperfect. I really thought these lights would be plenty bright. It's just funny I mean, it's supposed to be made for this purpose. It's an old light table. I guess they call it a digital presenter. It doesn't work as a digital presenter anymore, though. So I have a webcam attached to it. But anyway, yeah, enough. We'll just say that's enough. Step one, but that's understanding force bit is really mass bit, and the things we call, that we think of as matter, can be considered as almost irrelevant, in the sense that their only relevancy is they allow the force bits to interact with each other. The force bits can't interact, gravity can't interact with itself It can only interact when it hits one of these bits. It can only get trapped then, and absorbed. And so their only use is their capacity to create traps, essentially. Yeah, I mean, it's probably enough of a way to say it. So, till next time and such. That's good enough. I'll work on it. Mostly.